Hi everyone, welcome to this super exciting webinar. I am Wim Oudenaert, I'm CEO and co-founder at AM Team. It's a big pleasure to be welcoming you in this webinar. We have a lot of people subscribed over 150, and as usual, they are coming from a lot of different countries, so it's even a lot of different time zones. So quite an international audience. A huge variety of audience and also a lot of water companies represented in this webinar. So yeah, the AMOZONE webinar series has become a thing. Yeah? This is not the first time we do it. It has become a real series. You can visit all of those webinars on our YouTube channel. Huh? And this time, today, we are going to talk about smart planning and design, and we will be traveling to Germany. More on that very soon. Here's the menu for today. So we will be starting with a small intro on our company and the challenges many utilities face when it comes to advanced treatment. And then we will go see the overview of AMOZONE applications. So AMOZONE is the digital modeling solution our company has been developing and has been applying at many sites worldwide. Then, of course, the most exciting part of this webinar comes a case study with the German utility EGLV. So they will be explaining how they tackled the project at their biggest facility in Germany. It's a plant of over 1 million population equivalent. And then we will also not only look from the utilities perspective, but we will also, of course, show the results, what came out there and how did this influence the decision making in the quaternary treatments. Then we will also introduce a little bit of findings. So we will keep bringing up these learnings throughout the years, and we will talk about small scale to big scale and how do you extrapolate and some major lessons learned. So during the webinar, there will also be a couple of polls, so you will be able to vote. You will see the poll on your screen and just be able to pick the answer, multiple answers very often. And if you have questions, please ask them. We invite you to ask many questions and use the Q&A window. So if you hover over your screen, you will see Q&A, and that's where you can really ask your questions. We will bring them forward from time to time in the webinar. So we will go now to the speakers. So I already introduced myself. I am CEO and co-founder at AM Team. I will be moderating today, and I have a couple of colleagues here. So the first one is Jessica. She is calling in from Italy, and Jessica is advanced modeling engineer. She has also been working on this project, so a lot of experience with modeling in general and modeling on this quaternary treatments. Even a PhD on the topic, I should say. Same as me, actually. And Peter is our next colleague. He is the VP Sales and Solutions, working with a huge amount of customers. Some of you might know Peter because he's involved in a lot of different stuff and interactions. And Peter will also be presenting part of the webinar. And then we have also our guest speaker. Very exciting to have Thorsten Lind joining us today. So he's project coordinator at EGLV, and Thorsten will be talking on this project, about this project from the utilities perspective. So yeah, Thorsten, thanks again for joining us today. We are super excited, and there's a reason probably many people have signed up, because it's always interesting to learn from the practitioner's point of view. So yeah, very exciting about this webinar. So yeah, I will give the floor to Peter. Peter will start with the introduction. So Peter, the floor is yours.
Yes, thank you, Wim. So hello, everybody. So indeed, I will introduce you a little bit to the topic of today. And yeah, first one slide in general on who AM Team is, because yeah, there are some new people joining the webinar that might not know AM Team yet. So AM Team is actually a company focused on modeling services and digital twin solutions to tackle the water industry's biggest challenges. Of course, the topic of today is micropollutant removal. So this is yeah, one of those challenges. And yeah, where we focus on with our company, we actually help water utilities maximizing today and anticipating for tomorrow. And we do that by yeah, using models and digital twin solutions, and yeah, having models that are really fit for purpose. So tailored to the needs of our customers. And typically we apply those models in planning stages to help making decisions in the early stage of a project. For example, should I go for ozone or another technology to remove micropollutants? But also in the design phase to help optimizing the design and de-risk the design. And in operational stages to help the operators, the process engineers to have an efficient process. We're based in Belgium, but we have some colleagues working from Italy and other parts of the world. But we also have a very global reach. So we work, we worked already in more than 24 countries and worked at more than 200 plants worldwide. The key solutions we typically apply are full treatment plant modeling, as well on the drinking water side as on the wastewater treatment side, including digital twins. CFD, which is all about computational fluid dynamics and how the water flows in a reactor, how everything mixes, how particles mix, etc. And then two key solutions are AMOZONE, which is the topic of today, which is all about advanced treatment, but also AMNOXA, which is all about biological nutrient removal and optimizing effluent quality, minimizing N2O emissions, and optimizing the efficiency of plants. But today the focus is, of course, on this part. It's on the AMOZONE part. Like Wim already mentioned earlier, it's not the first webinar. There is a lot of content already on our YouTube channel. So please have a look there if you want more content after this hour. Let's now start with the challenges utilities have when they need to think about quaternary treatment and the removal of micropollutants. And we will zoom in specifically also on the ozonation and advanced oxidation topic. And one of the biggest, or the first challenges when you need to start planning for such a technology is, every water matrix is unique. Every effluent from a wastewater treatment plant is different. It's all about the organics, the inorganics, the ammonia, the temperature, pH, so many different variables that will determine how you will need to design your ozone, how high your bromate can be, and all these kind of things. So that makes it hard to just extrapolate from one plant to another plant. And then, if you can do lab tests or pilots. But lab tests sometimes still give you a lot of questions are still unanswered after a lab test. And piloting the same story, and it also takes it takes long and it's quite expensive. And utilities don't always have that time. So this is one of the typical challenges we see a lot at utilities. And then when you really go to the design stage, designing such a full-scale plant is always a balancing act. How do you design for optimal performance, the removal of micropollutants, mass transfer of your system, while keeping your byproducts like bromate as low as possible? And then, how do you balance CapEx and OpEx? So it's a continuous balancing act where a lot of decisions have to be taken. And then, when you operate such a plant, but also during piloting, key variables like bromates and micropollutants are actually hard to measure. There's not an easy sensor to measure those kind of things. So these were a bit the challenges, and maybe we can already go to the first poll question, because we have foreseen a poll. So if you look at those challenges, which one of those challenges do you recognize as the most significant when you need to plan or design such a plant? Is it every water matrix is unique? Is it the lab tests leave many questions still unanswered? Pilot tests take long and are expensive? Design is a balancing act between the CapEx, OpEx, performance, and byproducts? Or the key variables are hard and expensive to measure? Or maybe other? So you can vote. I think you can even tick multiple boxes. And still waiting for the results. Okay. So yeah, now we see the results. So yeah, what we see is that indeed a lot of you indicate that every water matrix is unique. All about the design, that this is indeed a balancing act, and that the key variables are hard and expensive to measure. Okay, but a lot of you ticked a lot of boxes, I see. So I think yeah, a lot of the challenges are yeah, really living in the utilities. Huh? I'm curious what the other is, so please don't hesitate to put this in the Q&A. Okay, so that's actually why we developed, yeah, already more than 10 years ago, actually, the AMOZONE model, which is an engineering model for ozonation and advanced oxidation processes to actually help utilities with those challenges. So this model it's a mechanistic model, which means it's based on science and on the chemistry behind ozonation and advanced oxidation. So yeah, all that chemistry is behind that. And currently we already applied that model actually to yeah, more than 40 plants all over the world, as well on wastewater as on drinking water. So also for disinfection purposes, for example, in planning, design, and operational stages. The model itself has actually two kind of appearances. So you can use it as a process model or as a dynamic digital twin model in the planning stage or in the conceptual design stage or the digital twin stage, let's say. So then you can make predictions over time of your bromate and micropollutants. But you can also, or we also integrate it actually in CFD, so that it gives you in 3D a picture of your plant and can be really used to optimally design your reactor. You will see later on throughout the webinar how these things can be applied. Yeah, what is the input and the output of this AMOZONE model? So of course it needs influent data, so DOC, the micropollutants at the influence sites, bromide concentrations, alkalinity, temperature, pH, and some nitrogen species that are quite important to take into account. And there are also others still included in the model. And then it needs operational and design data. So the volumes of your plants, the ozone dose you apply, are you, for example, dosing additional chemicals and these kind of things. And based on that, the model, the AMOZONE model, makes predictions of micropollutant removal. So there are more than 100 components in the model. And it makes predictions of bromate and dissolved ozone concentrations in the reactor. And you can calculate mass transfer efficiency and disinfection performance. So that's a bit of a general yeah, capability of the model. And then you saw the challenges. So we apply actually this model in the planning stage, where we use models to actually complement or replace piloting by doing virtual piloting. And we apply the model in the conceptual and detailed design phase to really de-risk the design of a plant. And we apply the models as digital twins to help optimizing the operation of the plant. Today, the case from that Thorsten will present and Jessica will present is actually about piloting and virtual process design. It's a combination of both, because we help designing a pilot plant, and that's where Thorsten will now talk about. So I give the floor to Thorsten Lind from Genossenschaft und Lippenverband. So Thorsten is there, the project coordinator of this project, and he will explain you more about that. The floor is yours.
Okay. Good afternoon, everyone. My name is Thorsten Lind. I work for the EGLV, or Emscher Genossenschaft Lippeverband, how you pronounce that correctly in German. We are the largest wastewater treatment plant in Germany, and I will today talk about how we are preparing for the quaternary treatment. This is particularly challenging on this location, and how we use the CFD modeling from AM team to improve our initial planning and got to a way better result than what would have come out without the CFD modeling. So who are we? Where are we located? We are in the middle west of Germany, And we consist of two public wastewater management association that are governed under one common structure. That's why there is this very long name, Emscher Genossenschaft Lippeverband. Emscher, the first part of the first word, is the river that passes through the blue part, and Lippe is the river's name that passed through the green part. We cover over 4,000 square kilometer of catchment area with a population of 3.5 million. So that's nearly 5% of Germany's population. It is the former coal and mining area, which is why there was initial founding of the wastewater association in the 19th century, because wastewater became a real problem there. It all went through the open water rivers, and it stayed this for a very long time. Just in the last 30 years, the EGLV managed to bring everything underground, and we now do have a network of 430 kilometer underground piping, and the rivers are now wastewater free. But that was not the case before. And in particular, we also set up 4 large-scale wastewater treatment plants. And the one we talk about today is the largest one. It's the one close to the city of Bottrop. It has a capacity of 1.3 p population equivalent, and is located right next to the river Emscher. So in a dry weather season, we, with our regular wastewater, do a substantial part of the water that then is discharged into the Emscher River, which is why we need to take care of the quality of the discharged water much more. And we now have a new regulation in the European Union saying that large-scale plants have to implement the quaternary treatment step until the year 2033. Its purpose is to remove the micropollutants by at least 80%. There is a directive for it named CARL. CARL is the abbreviation for Kommunale Abwasserrichtlinie, a very long German word. It basically means Urban Wastewater Directive. And this is what we need to fulfill, but we have some very specific site challenges and a preferred treatment version, which is we want to do the quaternary treatment with ozone and sand. There is other treatment versions that are more textbook, but we would like to do the ozone sand version. And our particular challenge is that the wastewater that arrives at the treatment plant in Bottrop has high loads of bromide. Bromide itself is not a problem, but if you treat it with ozone, it oxidizes into bromate, and bromate is highly carcinogenic, which is why the authorities are not very keen on this method. There's other methods where it's more well known that this problem does not occur, or you get rid of the problem with the bromate formation. Nonetheless, we really would like to do the ozone sand version. Major reason is it is more environmental friendly than using the granulite active carbon. It needs less space than the other treatment versions, and we do have a particular problem with footprint or with space on site. And third, we want to be more independent of supply chains. So we discussed this a lot with authorities, and yeah, because of the high bromate loads, they said, okay, how can we cannot allow this without any proof that you can manage the directive with the 80% micropollutant removal, and that you can keep the bromate level at a very low level. The only threshold they have in mind is that for drinking water, which is a bit exaggerating given that we are talking about wastewater. But if we would reach the threshold of drinking water, they said, then of course we can also grant you the permit for ozone Z. So we thought we should test that first because the large-scale quaternary treatment will cost something between 150 to 200 million. This is a very substantial money that will come from our members. And so the idea is we first do a pilot project that covers about 3% of the usual wastewater. And with this pilot project, we will test in parallel our preferred version, the ozone sand. We will also test ozone and the granulate active carbon. And we will test a third version, which is called ozone strong water, to see if the results hold up and then make the decision on how we are doing the large scale. So when we were thinking about this pilot project, we were wondering about the size, the dimensions, the length, and it occurred to us regarding the depth of the water, we need to do it one-on-one with the large scale, but we probably can have some improvements on the reaction chambers for the ozone injection. And this is where the CFD modeling came in. So with the CFD modeling, we thought we could see how the flow in the pilot project will look like. And we were wondering if there is room for improvement on how we are doing the ozone injection. So as a public company, everything needs to go through a tender, or we need at least a few offers from service providers who can do that. And me and my colleagues, we interviewed quite some companies for this. And then we also came into contact with AM team and learned that they had done this in the past before. And actually in the initial interview already gave us almost the solution to our problem. So we chose AM team and we discussed with them our initial design. They then took this initial design, run it through their model and showed us over and over again how we can improve this. Jessica will talk about this after me, so I will not go into detail, but to give you a summary, the reactor could be much shorter than we thought to. We were initially planning 8 to 10 chambers. We now know we can do it with 6. We will, to calm down the authorities, we will still build 8 chambers, but given the CFD modeling, we will be good with 6. There will be 4 diffusion parts. So initially we thought we would inject countercurrent the ozone in the very first chamber. So you have seen this picture in the slides of Peter before. This is not the real pilot plant. It's just here for illustration. So you see how the residuals are dissolved over time. And initially we thought we just inject in the very first chamber countercurrent to dissolve the ozone and get rid of it through all the remaining chambers. Now the solution is that we will have a flexible setup with 4 diffusers in the first 4 chambers. And the results, given the CFD modeling, will be that we reach the 80% of removal of the micropollutant removal, and we will stay way under the threshold of the bromate formation that is important to the authorities. And the third one is that we already have some idea what is the optimal amount of ozone we should use in the pilot project. So after the modeling was done, the results were implemented in our initial planning. It changed the cube of what we were planning. The cube is now in construction. I do not have other pictures in just the CAD pictures. And we will have the ozone sand and the ozone granulate active carbon in parallel, and we will also have the strong water next to it. It's going to be finished in terms of construction by the end of Q2. So we want to start at Q3 this year with a year-round testing. And then a year after, we are going to present, we're going to summarize the results and we're going to present them to the authorities with the hope that they then will grant us our preferred version, ozone sand. And we will roll out this with other plants that we already have in operation. Yeah, this would be all. And I give back to Peter.
Thank you, Thorsten, for the introduction of the project. And I will take over with the details about the project and what we did for the ozone at the Bottrop pilot plant. So I will guide you step by step through the different phases of the project, starting from step 1, which was grounded on the batch tests we performed together with the laboratory in Germany, the Utah lab. And here we performed the batch test. As you can see here in this figure, we inject ozone into in a controlled way into a water sample of the water matrix sampled at Bottrop at the effluent. And in these figures, you can see the results for a high ozone dose that we tested was 0.6 grams of ozone per grams of DOC. In particular, if we look at on the left graph, you can see the residual of ozone in water in time. So there's the decay of ozone. And we calibrated our AMOZONE model on these lab data. So we calibrate the ozone residuals and also the bromate formation that we could see building up in time as a byproduct of ozonation. Starting from this point, we could calibrate the model accurately on the water matrix of Bottrop effluent, and we could simulate in the second phase with the process model a preliminary. We could do a preliminary study focusing first on the residual of ozone at the effluent in order to assess whether the volume estimated at first was enough to grant a low residual in the effluent, and whether there could be the possibility of reducing the volume and as well the costs related to the construction of the reactor. So in this study, we could see that actually the initial volume was resulting in very low residuals, and there was room to reduce the volume further with still granting low residuals in the effluent. At the same time, we wanted to test different specific ozone doses and different DOC levels to see the bromate formation that could be experienced at the Bottrop once the reactor would be built. And as you can see on the right, the bromate formation at the lower ozone dose of 0.4 was below 1 microgram per liter at any DOC level tested, while with the higher ozone dose, the bromate formation was below 4 microgram per liter. So still a feasible ozone dose in order to stay below the limit of 10 microgram per liter that was present for the Bottrop effluent. So in this feasibility study, in step 2, we could get the first insights. And then once we move to step 3, so with the CFD AMOZONE model, we coupled the kinetic modeling of AMOZONE that was previously calibrated on the batch test. We coupled it with the CFD in order to see in detail in the space in the reactor how the different concentrations of ozone and bromide and bromate and micropollutant removal would look like. So what you can see here in this image is the side view of the pilot reactor at Bottrop, the initial design. And here we had bromide in the influent of 350 microgram per liter. Then there was a counter-current configuration with the two injection chamber, the first one and the third one. And with an ozone dose of 0.4, we got an effluent bromate of 3.4 microgram per liter. We could see with this CFD analysis that the average removal of the micropollutants of the current list was around 70%. So it was below the 80% target. And we could also see that actually after the fourth chamber, there was nothing happening. So bromate was already formed, micropollutants removal was already reached as in the effluent, and also the ozone residuals were almost zero already after the fourth chamber. So we could see that there was actually room for optimization. And in the subsequent step 4, we actually tested more scenarios, testing different designs. This one is the last one we chose, so the one performing better. And as you can see, we have reduced the number of chambers from 8 to 6, and we have increased the number of injection chambers. So we have diffusers in all the 4 forced chambers. In this way, we could actually reduce the local ozone concentrations compared to the initial design, thanks to the fact that there are more diffusers that can deliver the same gas flow. So the ozone concentration is actually lower. And then in this way, with diffusers in 4 continuous chambers, the EGLV can also try to operate the reactor in different ways. So the counter current, which is something typically used in the past for many years. This is the design typically in place from previous reactors, where the flow of water is in a counter current direction compared to the gas flow. So the water flows down in the first chamber while the air flows towards the top. And this is the counter current in which only the diffusers in chamber 1 and chamber 3 are active. While there are also other ways we can operate the reactor, which is the co-current design, where the water and the gas flow in the same direction. So only diffusers in the second and fourth chambers are active. And then we also modeled and tested the reactor in the hybrid configuration, where we have the diffusers operating in all the 4 chambers. So we actually have at the same time the counter current and co-current operation. You can see here the results for the ozone gas concentration. So you see in the counter current configuration, we have ozone only injected in the first and third chamber, while in co-current second and fourth, and hybrid, we have the ozone in all the 4 chambers. What we can observe is the difference in the gas plume. If we look at the counter current, the gas is more pushed towards the bottom, while in the co-current configuration, due to the same flow direction of water and gas, the ozone is more spread along the height of the reactor. Similarly, we can observe the same thing for the ozone concentration in the water. So different ozone with the counter current and the co-current, we have the same behavior with the ozone more pushed towards the bottom in the counter current configuration, while in the co-current is more spread across the height of the reactor. And this actually results in a different impact on bromate formation, because due to this more concentration of ozone in the counter current situation, we have also higher bromate formation due to this higher local concentrations. That results in the end in 1.4 microgram per liter of bromate, which is lower with respect to the initial configuration of the reactor, much lower. It was initially around 3 microgram per liter, and this is thanks to the more diffusers we have put in place and the different design used. But we can also actually improve more the performance in terms of bromate formation using co-current or hybrid configuration. Thanks to this major spread of ozone concentration in the co-current, we are below the counter-current emission of bromate, and we reach 1.1 microgram per liter. But then with the hybrid configuration, by spreading the gas flow between the 4 chambers, we have even lower ozone concentrations, and we reach 0.8 microgram per liter of bromate in the effluent, which is very well below the threshold of 10 microgram per liter. Then we also focused on the performance of the reactor in terms of micropollutant removal. Here you see the example of 2 micropollutants, metoprolol and clarithromycin. They are 2 very different micropollutants responding differently to ozonation, so that's why we chose those. But for both of them, you can see that with respect to the initial design, we could detect an increase in performance, so an increase in removal of almost 5% with the new design, with similar efficiency for the different operations. So countercurrent, co-current, and hybrid actually gave a similar efficiency. And also in terms of bromate formation, if we look at the hybrid configuration, we actually could reach a 75% reduction of bromate, which was very significant due to the restriction and the high levels of bromide in the influent. And also thanks to what we could observe in terms of ozone residuals, but also if we look at the micropollutant removal and bromate formation, we see after the 4th chamber, the results are quite similar and stays constant in the subsequent chambers. So we actually could indicate still a large improvement in reducing the footprint and at the same time lowering the costs. So it's actually feasible to reduce the footprint thanks to this analysis. The fact that the water matrix is actually eating very fast the ozone, the residuals in the end are quite low already after injection. And as a last step in this project, we actually wanted to move from the CFD that in which we could test a specific fixed condition, so with a specific level of water quality in terms of DOC, ammonia, nitrite. We wanted to actually see what happens during the real operation of the plant in the future. We know the influent, the secondary effluent is not with a steady state water quality, but we might experience peaks in DOC, ammonia, nitrite that are actually very well affecting then the results in terms of bromate and micropollutant removal. And also there might be spikes in bromide at the plant, as Thorsten anticipated. So we wanted to simulate these more than 70 days of dynamic influent. And here you can see the results we performed at different ozone doses. So we wanted to see if we then are going for a higher ozone dose, what happens in bromate at a different water quality. There might be the risk maybe in reaching the threshold of 10 or also having higher concentrations. But the answer was no. Even at the higher ozone dose, the bromate threshold of 10 was actually never reached. And at the same time, also, you can see in the graph at the bottom, we tested different ozone doses with different bromide in the inlet. And here we actually could assess a good range for EGLV to operate the plant that was between 0.45 and 0.65 grams of ozone per grams of DOC, which allows at the same time to stay below 10 microgram per liter of bromate, but also to reach the target of the 80% removal of micropollutants. And on the right, you can see the two series are actually representing the average for the micropollutants of the CAR list, but also we wanted to assess as well the removal, the average removal for the 12 micropollutants of the European Water Directive. So we were able to actually also report and suggest an optimal dose range. And this, at the same time, with the dynamic process model, we could actually prepare a kind of digital twin that could be that can be used by EGLV during the piloting phase, during the operation of the pilot. So this was the last step of the project. If you have some questions, we can answer them at this stage or later.
Okay, so we had now the case. Now I just want to highlight something, and that how the design of your lab tests or your pilot tests can really influence the outcomes. And yeah, we will also still launch a poll question. So yeah, before designing such an ozonation reactor, and you can do lab tests, and you can do a batch test like this. So you add a separate sample to the water. I would not do it like this, but I mean, like Jessica already showed earlier, you can also do a kind of bench scale test in the lab, or you can really do yeah, pilots on site. So different strategies can be followed. Maybe let's first ask the audience which testing that you would rely on before designing your ozonation plants. Would you say no additional testing? Would you say lab testing? Would you say pilot testing or other? It's quite divided, but some people really, yeah, I think the majority goes for pilots. Good. Well, I just want to show you one slide on a study we did together with Utah and the lab in Germany, and with Air Liquide, and also with samples from multiple plants, including waterborne to Dommel. And this is actually a scientific paper on the variability by the assessment of bromate formation. So how you do the assessment also will have an influence on your results. What we did there is, so the lab collected samples from multiple wastewater treatment plants, and then they added a dose, 5 milligrams ozone per liter, with a certain stock solution. So you inject with a stock solution of ozone of 50 milligrams ozone per liter in the stock solution, and you inject that over 5 times, and you make sure that you have a dose of 5 milligrams per liter. This will give you a certain result in bromate. So that gives you an idea on the bromate formation potential. Now, if you do the same tests, but with a higher ozone dose, you see a logical result. You will see a higher bromate concentration. Now, what if you do this same test, but instead of using the 50 milligram ozone stock solution per liter, you use a 25 milligram? Then you really see quite a difference in bromate formation potential. And what if you inject in 20 seconds instead of in 5 seconds? And so you do the same test, but slower. Then you see lower bromate formation. So this just to say that even how you do your batch testing, how you do your bench scale testing, how you do your piloting, everything will have, yeah, how you do it will really determine the outcomes. And from there on, you then need to scale up to your full scale installation. So yeah, your assumptions really matter here. And we did this, so these are real tests, but we also did this with the model. So we did the batch test with the model, and we saw the same results here. And this is also published scientifically in a paper in the Chemical Engineering Journal. So if you scan this QR code, yeah, you can read the results of this study. What I just want to say is that these batch and pilot tests are meant to gather information for future full scale, and can be really important. But yeah, often they are not representative to make this extrapolation. So yeah, be careful. Your assumptions matter. And this brings us to some summary slides. So what we want to say is if you start planning for such an installation and you're planning to do experiments, yeah, it's very smart to already include the modeling from the start, because you can really benefit from using the lab tests or pilot tests together with modeling to help you scale up to your future full-scale installation. So we can help in the virtual piloting phase there. We can help in the detailed design phase, and then later on you can reuse the model as a digital twin. And then one thing I also wanted to add is we mainly focused on ozonation, but it actually also includes other advanced oxidation technologies like peroxides or UV, and we're also working on a granular activated carbon model, so that you can also dynamically predict breakthrough curves of different micropollutants. So we can already use that model also in a virtual piloting context to give you the full picture of what if you would combine ozone plus GAC. And maybe I will first give it to Wim for the key lessons learned, and then we can still end with some Q&A.
Yeah, good idea, Peter. We can handle these remaining questions at the end. These are the last two slides, so we will for sure have some residual time for the Q&A. And also, if you have additional questions, do not hesitate. We will, let's say, it takes 5 to 10 minutes extra if needed. Okay. Yeah, key lessons learned. Key lessons learned. AMOZONE was already in development before our company was founded. So all I can say is that this has been a journey on purpose, because some people were developing this model. It was actually including myself. We're thinking, yeah, these systems, the design, the decision making needs to be enhanced. How can we do that? And today we can say, I think, that the AMOZONE solution has emerged as quite a reference solution. We work with a lot of big companies in the market, with a huge amount of utilities as well. And we helped designing and deciding on more than 40 full-scale facilities, not only in Europe, but even across Europe. All I can say is that the earlier AMOZONE is being used, the more value is brought. So all of these stages Peter has presented are very useful, but all I can say is don't wait for the first data even. Go for very, very early stage use, because the model will only improve and be carried on, as the stages progresses. So that's really a point I cannot address enough. Smart design and operation also enable ozonation even at high bromide concentrations. We have seen it. We helped designing plants that are operating at bromide with over 1,000 micrograms per liter. You would say in the past, yeah, this is not feasible, but also Peter has shown the limitations of batch and pilot testing. And if the design and operation is smart, it can really, really work very well. So also there we help to reduce a little bit the barriers of the implementation of this technology. Yeah, using the model in design stage is probably so much de-risking and so much improvement at many fronts. We have seen it across all of those cases. Not only you will meet your compliance, okay, for example, 80% removal, 85% removal, but also you will keep your bromate low if that's a point. Sometimes it's not an issue, but also the cost optimization is quite significant, while you also de-risk the design, because we should not forget these advanced treatments cost a lot of money. It's a lot of taxpayer money. You don't build such a plant often for 1 million euros. It's way more than that. And it has to operate for 20 years, 25 years. So the decisions are so crucial. Once it's built, it is hard to go back. So we can highly recommend this, bringing into the design stage, this tool. I think also Thorsten exemplified that in the presentation. Yeah, the extrapolation from batch, pilot to full scale was mentioned, of course. And another thing I wanted to talk, and these are the last two bullet points. you would say, okay, yeah, we are used to work like this. Or, for example, engineering companies might say, yeah, we are used to work like this. We realize that we as a company now provide, let's say, an additional feature in engineering projects. I think it is very important that the utility really stresses the importance of including AMOZONE, because the market, of course, has a certain way of working. Engineering people are very stressed, they don't have time. Um, the reflex would not be, okay, bring on this additional tool. However, we see in all of these projects, once we go through the process, the project does get very, very efficient as well. So decision making in the project, in design projects, gets enhanced. And we have very good collaborations right now with engineering companies as well that initially were very skeptical, but once we were pulled on, they saw, okay, we have a significant risk reduction and it's leading to better results. And we are all learning way more. So I also want to stress that, because it's a market barrier. Even though the technologies can be powerful, we have market barriers, and these last points can really help removing them. In the end, it's a win-win-win situation between many parties. Okay, I don't know if there's an additional slide. Yeah, it's how to work with us. Either we are working with two business models. The dominant one is modeling services. It's project-based. We are pulled in projects, either are under direct contracting with utilities, for example, with EGLV, or as a subcontractor of bigger consortia. There are many ways possible. And in that service, of course, we provide the virtual piloting, the virtual design, and we are part of the team. And then we also have the other business model where once the plant is operational, or once the design has been established, the model can also be handed over to the utility, so the utility staff can play with it. And this is what we call a digital twin, either for online use or offline use. So we have various cases where people are right now using the model themselves to learn, to get training, and to also enhance the operational decision making. So two business models, the one is a project-based, the second one is a license, but two are possible, and the second one is a very nice continuation of the first one. These are the two business models that we provide. Okay, so I think this brings us to the end of the webinar. For the people that have to leave now,